Good afternoon. I'm Dhanjit Talukdar from Department of Physics, Textile University, and my topic of presentation is investigation of structural, electronic, and optical properties of lithium doped hexagonal boron nitride through Green's function. Well, these are the timeline, and so without further ado, let me introduce the material first. So hexagonal boron nitride, it is a hexagonal phase structure material. It has two atoms in its unit cell, one boron, one nitrogen atom. It is a layer structure material with a separation of layer separation of 3.22 Armstrong, and the energy band gap of the material is direct at K point, and which is around 7.43 electron volt, and indirect band gap is around 5.72 electron volt along K gamma direction. So work plan, we have actually used quantum espresso first principle calculations to optimize the structures, and then we have calculated the electronic band structure using density functional theory using this quantum espresso software. The van der Waals interaction between the layers is actually taken care by DFT D3 term, and most importantly, the electron-electron and electron-ion interaction, it is taken care by Green's function theory. Later on, we have calculated the optical properties, which is calculated by solving the Bethe-Selter equation. Well, the main problem in DFT is that it actually excludes the electron-electron and electron-ion interaction, which is being incorporated in ZW theory. So to have a better match with the experimental data, people nowadays opt for ZW plus density functional theory approximation. So that is what we have actually opted. For example, we have calculated the band structure of pristine hexagonal boron nitride using this local density approximation. This is actually conventional DFT approach. So if we include these quasi-particle interactions, so we can clearly see that when we calculated using this local density approximation method, the direct band gap, this blue line, it was around this, it was a direct band gap material, which is around this K point. When we include this ZW approximation, that means this electron-electron and electron-ion, this quasi-particle correction are actually included. So it is actually showing that it is an indirect band gap material. That means this quasi-particle correction not only quantitatively enhances the electronic properties, it also qualitatively enhances the electronic properties as well. So that's what we are going to use to study this optical properties. So this is for pristine hexagonal boron nitride monolayer. So we have seen that the indirect band gap, that is around 5.71 electron volt, direct band gap 7.43 electron volt. So if we subtract that from this, if we subtract the optical band gap, this is lying around just pointer here. So which is shown around here. So this is the optical band gap. So if we subtract this optical band gap from the direct band gap, we get the exciton binding energy of the material, which is around 1.70 electron volt. So what we have done in this particular work is we have doped a lithium into this particular system. So we can dope the lithium in two sites. One is nitrogen side, one is boron side. So we have seen that when we dope the lithium into nitrogen side, it is energetically more favorable. In addition, the vacancy formation energy for nitrogen is also less as compared to this boron vacancy formation or di vacancy formation energy. So in our further studies, we will be studying the lithium dope system, but in hexagonal boron nitride, this is substituted by replacing a nitrogen atom. Well, we have calculated molecular dynamics simulation to see the stability of the system at room temperature. So minimal fluctuations in this particular two diagrams actually shows that the system, that is lithium dope system, is actually stable at room temperature. And now the next question is whether the system is air stable or not. So we have exposed the particular system to nitrogen and oxygen molecules, which has the highest abundance in this particular atmosphere. So we see that the structural integrity of the system actually remains even after exposing them to this nitrogen and oxygen atom. So we can say that it is indeed air stable. Well, so coming to the electronic properties, so we have calculated the ZW band structure of the material. So when we dope the system with a lithium atom, we see that two defect bands actually arises here within this forbidden gap of the material. So hexagonal boron nitride has a very wide band gap. It is around 6.5 or something like that. So what happens is that it actually introduces two defect band states. So one above the Fermi level, one below the Fermi level. So if we zoom into the system, we can actually, for simplicity, divide this particular band structure into four segments. So this is the intrinsic part of the system. So intrinsic valence band and intrinsic conduction band. Then we have two defect bands that is actually incorporated because of the lithium doping. So this particular defect band in this valence band region, it is coming because of the lithium s orbital, and this particular band over here in the conduction band, it is coming because of the nitrogen 2p orbital. So let us name them so that we can actually go for the further studies. So we have named them as X and Y, these defect bands, and this particular intrinsic states we have naming them as X star and Y star. So this is the band gap and we have tabulated the values of the band gap of this particular different defect states in between these intra gap states. So we have seen that this GW incorporation actually enhances the uh, electronic properties, a study of electronic properties. That is, we can see that in between this X star and Y star states, if we see that using LDA, we have calculated the band gap is around at P point. So which is P point is shown around here. But if we include GW, it shows that the band gap is at N point of the system. So it is actually right here. So it moves towards the M point of the system. And next, this is a schematic diagram showing how LDA versus GW band structure basically looks like. So we can see that the GW band structure actually, GW calculation or the quasi-particle correction actually widens up the band gap of the material to better match with the experimental results. Well, next we have calculated the optical spectrum, optical absorption spectrum of the material. So because of these two defect states, this X state and Y state, we can see that there are possibilities of intra-gap transitions for this optical spectrum. So transition may take place between this X and Y state, that is a defect state. So we have named it as a type A transition. Type B transition, it is actually taking place in between this X state and this intrinsic conduction band state, this X state and Y star state. And if we conclude this type C transition, it is taking place between this intrinsic valence band state to this defect state in the conduction band. So we see that the first excitonic peak arises at 1.61 electron volt. So, and the second one at 3.06 electron volt. So these are type A transition, and we have actually identified the different excitonic peaks in the diagram as well. So we have tabulated the data. In addition, we have also calculated the probability of finding the exciton in the system, concluding actually considering that the hole is fixed at a particular position. So for these different peak positions, these are the probability of finding the excitons in the system. Well, this is the tabulated data for the exciton peak in the different positions of the optical spectrum, along with their exciton binding energy, which is shown in the last column of the table. Well, coming to the conclusion, so what we have done over here is we have actually included quasi-particle corrected electronic and optical properties of lithium hexagonal boron nitride. And we see that the ultra-wide band gap of the material actually narrows down to 3.72 electron volt at K gamma point. The direct band gap arises at gamma point with energy band gap of 3.84 electron volt. So because of this narrowed band gap, it reflects in the optical properties. So first excitonic peak arises at 1.61 electron volt if we compare it to the pristine hexagonal boron nitride, where the lowest exciton peak arises at 5.5 electron volt. So this means that there is a redshifting of optical band gap from deep ultraviolet region to visible spectrum if we dope the system with a lithium atom. So these are some of the references.
Good afternoon, everyone. So myself, Dr. Dimpi Paul, Assistant Professor, Department of Physics, Pathakanti College, Assam. So I'm representing my college, and it's a very optical fiber based sensing material device. I have not exactly device, a setup I have made up with the help of few of my students. So it is basically dealt with the displacement sensor by conventional optical fiber with different reflectometer for in presence of a dissimilar media. So before starting that, I would like to say what will be my points to elaborate. First, I will discuss about the introduction, how the optical fiber can work, and secondly, I'll give a brief about the experimental overview and the result that we have observed during the experimentation and the conclusion we have got, and finally, I'll discuss a few lines about the future prospect. So, first of all, I would like to give an introduction to total internal reflection. Why I'm stressing it to total internal reflection is that this is the basic phenomenon via which basically the conventional fiber works. Now, this is the phenomenon that has been used during our experiment as well. So, first of all, in the year of 1841, the total internal reflection phenomenon coined out by Jean Daniel. So during this process, the total internal reflection, we see that if there is a difference in refractive index between the sand core and the cladding, I'll come to that later on. Why I'm stressing on to core and cladding, the two different medium, that will also be elaborated by me later on. So total internal reflection phenomenon is a phenomenon in which light is tend to travel from one one part, one end to another end without with a very few leakage, and it can transmit information. So that is our main funda. We can experimentally do the experimentally prove that if we can sense anything, if you want to sense the refractive change as well, we can use that particular phenomenon of optical fiber. So in the introduction part, I would also like to point out that total refraction phenomenon also depend on two main angles. One is acceptance angle and another one is critical angle. Here we can see that the N2 and N1. Why N2 and N1? The cladding, the, as I have mentioned a few minutes back, that the cladding region has a refractive index, and the core region from which the information can be transmitted should have a difference in refractive indexes. This is the basic thing with which we can use this as sensing purposes. So and there are few types of optical fibers, single mode and multi-mode. Basically, during my experiment, I have used multi-mode step index fiber, in which we basically has a core and a cladding, which has a refractive index difference near about say few ranges of difference in refractive indexes. So from that we can actually transmit the information from one end to another end. So the in the experimental overview, before starting the experimental overview, the refractive index, as well as if we remove the core, remove the cladding part of an optical fiber, that also has an impact, because the evanescent field, that is the corresponding media nearby the core material, is also important, because it actually impact on the changes that carries the information from the fiber. So that's how we can actually use the optical fiber in our communication system. So in sensing, as I've already mentioned here, I have shown via a diagram that evanescent wave, how it works. Actually, if I'm removing cladding, few parts of the transmitted light from the core uh, depth or interfere into the cladding part, and this actually can uh, observe, and this can actually gives us the information about the changes in the fiber, changes in the transmitted information, using and that can be utilized for sensing purposes. It can be taken, the output can be taken out based on intensity, wavelength, and also in terms of voltages. So in my experimentation, I have used an LDR, light detecting refractive resistors, and using that I have taken out the information in terms of intensity. So first of all, in the experimental overview, I would like to point out that I have used two optical fiber, one as transmitting optical fiber, and another one is as receiving fiber. In the transmitting optical fiber, the optical fiber has in, as shown in the figure. If you can see the input fiber, the light coming in through the input fiber goes to via a reflector. It transmitted the information to the receiving fiber, so that it receive a certain information, and we can calculate the displacement. Since I'm dealing with the displacement, more the displacement is, less intensity the output will give, and automatically it can observe the changes. And similarly, if we bring the input as well as the receiving fiber towards the reflectometer, automatically it intensity increases, and we get the maximized input output as from the LDR. So this is the basic part we have used to transmit information. Three different types of reflectometer have been used: convex, concave, and plane mirror. So during the experiment, we have seen that the principle, as I've already mentioned, there are two basic optical fiber has been used, and in that optical fiber, I would like to point out one important point, is that the evanescent field. Since if we you can see in the chamber, there is a chamber in which I have changes the as I have mentioned earlier, that evanescent wave also has an impact on changing the information surrounding the optical fiber. So in that medium, I have changes three different dissimilar media I have point out. One in the without keeping anything, that is in EO medium, I have checked out the information, the displacement, how much displacement it can detect via the receiving fiber. Secondly, I have put it in a sugar solution. Thirdly, in a dilute ethanol. So three different types of this thing medium has been changed so that I can observe the changes of that particular setup in every medium. And also we have seen that in every medium it has an impact, and it has a tendency to show us the displacement, how it deals with the displacement, or if I'm changing the displacement, how it can sense the displacement change via that setup. So in the working principle, I have already mentioned that I have used two different types of setup. The intensity is the main factor, which is basically we are collecting the information, and if the intensity is maximized, we can say that the the setup is working properly to detect the intensity of the particular of our sensing setup. So these are the results that we have observed in the ear medium. We have seen that in case of concave and convex fiber, concave and convex fiber is shown a deep in both the all the three, as I have observed, all the three of reflectometer plane, concave and convex, we have shown a deep because it has to go via that reflector. So it takes a time to reach the reflector, reach the receiving fiber from the transmitting fiber, so that it can transmit the information. So that is the reason why in every medium we have seen the one deep. But out of all the three, we can say that in case of your medium, water medium, and sugar solution, and the dilute ethanol was an additional experiment we have performed. We have seen that in convex mirror shown intensity more than that any of the two of like concave and plane. And out of the three concave is performing better than that plane mirror. So we can say that if we use any reflectometer, so convex can be a better performance, can show us the displacement response quickly as in comparison to concave and plane, because I have only used only three. And in all of the three medium, we have seen that in sugar solution, it is come out to be a displacement is quite visible than that of the other three. So these are the experimental data that I have calculated during my experimentation. And repeatability test has also been performed. Here also we can see that convex mirror shows better repeatability performance than that of the other two. And out of that plane, out of concave mirror, plane mirror is showing much more better result in repeatability than that of the concave mirror. Yes, and in the conclusion, I can say that this particular setup can be used to not only see the intensity, but also it can via the using the intensity, we can see the displacement, how more intense the particular fiber is. The displacement can be sensed easily, very easily, because the evanescent wave field has an impact on the change in medium corresponding to the nearby to the core medium, as we have changed the medium in terms of air, water, sugar solution, and ethanol. So in each respective medium, it shows a particular displacement change, and this change can be recorded, and this change can be utilized in another experimentation also. And out of all the three, I have already mentioned that convex mirror performance, I have found during my experiment that it is much more better than that out of the two. And but we can say that in terms of repeatability, plane mirror and convex mirror performance is better than that of the concave. So we can use these two mirror during our experimentation. So in near future, we would like to do the same performance we can perform for strain and pressure sensor. As a pressure sensor also we can use, and also I would like to use this particular setup for detecting the refractive index sensor, because as we know that the change in refractive index, as three dissimilar medium we have used, so change in refractive index also has an impact on this particular setup. So this whole setup can be used in refractive index sensor as well. So these are the future prospect what we can perform later on if
Thank you so much. Good afternoon,
Yes.
the chairperson, and like to acknowledge the organizing committee. So I'd like to present one of the work which my students has carried out. Like she's Midismita Borua. She just finished her PhD. So the title of the work goes as photocatalytic degradation of phenol wastewater by copper dope titanium dioxide activated carbon nanocomposite. So basically what we are doing is, like our group have been working on activated carbon. We use the activated carbon for environmental work, mostly the environmental remediation, removal of different pollutants or absorption. So we have extended the work. We started the work for photocatalysis. So one of the photocatalysts which we used is titanium dioxide. However, there's some problem associated with the titanium dioxide, which I'll be explaining in my subsequent slides. So what we did is, in order to do our photocatalysis, shifting from UV region to the visible region, what we've done is we have doped cobalt metal into the titanium dioxide, and we made the composite, based on the activated carbon surface, and that's how we have developed the catalyst and done the photocatalytic reactions and the degradation of phenol. So basically, there are a lot of conventional wastewater treatment procedures are available. All these things we know, that absorption, membrane filtration, electrocatalysis, the different techniques are already existing, and everybody is working on that. Each technique has got its own advantage and disadvantage. We thought of doing some environmental work based on photocatalysis, because the advantage of the photocatalysis is ultimately converts the pollutant into a harmless compound like carbon dioxide and water. So the basic principle of photocatalysis is, you need to use a light, a photon, and then electrons are excited from the valence bond to the conduction band, and then they create a sort of H plus and the electron pair. So this each level that goes for it ultimately it creates an OH radical, and that OH radical is responsible for degradation of the organic pollutant. It's a known fact, like organic pollutants get degraded by the OH radical, and it gives us the carbon dioxide and water. So as I told you in the beginning, we have used titanium dioxide for our work. However, since the titanium dioxide band gap is 3.2 electron volt, is basically gives the photocatalytic reaction only in the UV region. So, but we wanted to have the photocatalytic reaction in the visible region. So we need to reduce this particular band gap, and that is possible by doping a particular metal, like we have been doing with the different metals. In our case, we have used the cobalt metal. As I told you about the different photocatalysts, there are different photocatalysts are available to doing the photocatalytic reactions. But as in our case, we have taken the titanium dioxide, and I'd like to highlight these particular points because we have worked on these points. Like titanium dioxide, it gives the photocatalysis in the UV region. So we wanted to do the photocatalysis in the visible region. We wanted to shift to the visible region. And another problem with the titanium dioxide is when you use the titanium dioxide, it agglomerates, and that becomes very difficult to handle actually. So we wanted to avoid the agglomeration, and most of the people are using different surfaces for that to avoid the agglomeration. And since we have been working on the activated carbon, we have used the activated carbon at the surface, and then deposited on the activated carbon surface to avoid the agglomeration. And that's how we have done the photocatalytic reactions. And this is the known fact, like activated carbon, why we have used it, it has got a lot of porous structure, which can be used for this avoiding the agglomeration of the carbon surface, we have embedded into the activated carbon surface. So in present work, what we've done is we have basically doped the metal like titanium into the titanium dioxide, and this is supported on an activated carbon, and that's how we have developed the photocatalyst. And the advantage of taking a cobalt is here, because cobalt's radius is almost similar to the titanium, so it can easily replace in the in the structure of the titanium actually. And that's how the experimental procedure is, like titanium dioxide, and we've taken the activated carbon and the cobalt nitrate in situ, the normal official normal procedure. Then we've gone for the hydrothermal process, and ultimately we have synthesized the composite, and which has been characterized by different techniques. I need not discuss because there's only 10 or 12 minutes time is there. So there are different techniques normally used for characterization of different nanocomposite, for example, XRD, IR, SEM, EDX, all these things have been used. So here I like to just share this particular plot. For example, because our whole target was shifting the sort of photocatalysis from the UV to the visible region, and that was possible. You can see here, if you go for the TOX plot, and there you can find out the band gap of the composite, and band gap was basically shifted from 3.2, which is the titanium dioxide band gap, to 2.4 electron volt, and which has basically led us to do the photocatalytic reaction in the visible region. So this is one of the main story of our work. Like then subsequently we've gone for the degradation of the phenol. So I'm not going to discuss the different results here, because the phenol degradation is done with the different doses of the composite for different strength of the phenol solution for different times, and the whole purpose is to find out an optimum condition. So we have found, like the best condition was sort of where we could get the 100% degradation was for 20 ppm phenol solution for irradiation time, like exposure to 60 minutes at pH 2 with a nanocomposite dose of 0.35 gram. So here is very important to mention, like in order to confirm whether the degradation is taking place in the EV also, we have first initially, before going to the visible lamp, we have done the degradation process. We have irradiated the composite, the solution in the EV region, for a different time period, and hardly 0.8 or 0.08 or 0.07% decomposition basically took place, which confirms the photocatalytic reaction was not taking place in the UV region. And then subsequently we've done our reactions in the visible region, and these are some of the parameters. Like normally when you go for the photocatalytic reactions, we go for the kinetic studies, thermodynamic studies. This has been done. So here is very important to mention, like when you do the photocatalytic reactions, what are the different compounds or the minerals, like a different composition is forming in the reaction, because this is a complex reaction. Radical reactions are taking place. What actually it is forming in between is very difficult to identify. But we've gone for the GCMS, and we could find, from the mass spectroscopy, we could find there are formation of peroxy radicals, hydroquinone, malic acid, phenoxide ion, oxalic acid, formic acid, and which ultimately lastly leads to your water and carbon dioxide. These are the different products we got it from our GCMS. Here we have done some of the experiments to understand how sustainable the catalyst is, because if the catalyst is used only for one time and subsequently if it's not active, then the purpose will not be done. So we thought of reusing the catalyst for several times, and we could use up to 5 times. Like as I told you, the condition was for 20 ppm solution, so which was giving 100% degradation initially, and of course it is going down a little bit, but then after 5th cycle we could get it up to 85 to 87% degradation, which basically confirms the fact that the catalyst is basically quite efficient, and it can go for different cycles. It can be reused for several times. Also, in order to go for real test analysis, real case analysis, what we thought, why not let's study the photocatalytic degradation in the presence of different interfering ions. Basically, what will happen is that the different ions which basically can absorb the radicals. If the radicals are absorbed, the catalytic reactions will go down. And we have realized under different presence of different interfering ions, degradation is changing actually. Like for example, we found in the case of suppose if you take glycine. Glycine is basically known as an OH radical absorber. So if the OH radicals are mostly responsible for the oxidation, if the OH radical is absorbed, by glycine, definitely it is expected that the degradation efficiency will go down. So you can see in the graph, in presence of glycines, the degradation goes down almost 100% to 58%. So we have studied for different, interfering ions, and you can see the results here. Glycine gives the 58%, and some other thing is EDTA, which is also absorbs. It is known as the whole scavenger. So in presence of EDTA, also degradation is basically changes from 100%, it goes to almost 68%. So in last, or in conclusion, I can say, by doping the cobalt metal into the titanium dioxide, we could do the photocatalytic degradation in the shift from the UV region to the visible region. And we have developed a nanocomposite by putting this titanium dioxide doped with the cobalt metal into the carbon surface, and that's how the efficiency of the photocatalyst increases, because carbon surface gives a more surface area, which basically helps absorption of more pollutant, and ultimately it leads to the better photocatalytic performance of the catalyst which we've used. So that's all I wanted to share, and the work is still not yet published. It's just last month we have submitted a patent on this. So subsequently we are thinking of communicating the paper. Thank you so much.
Good evening to all of you. First of all, I'd like to thank the organizer of ICRTMD and the session chair. As you can see, the title of my talk is Defect-Rich Carbon Nanostructure-Based Hybrids, Possible Cold Cathode in Electron Microscope. Myself, Dr. Diptanil Banerjee, Associate Professor, Thin Film Nanotechnology Laboratory, Department of Physics, Tirthankar Mahavir University. This is the layout of my talk. First, the brief introduction, then aim and objective, result, discussions, and conclusions. Now, the material carbon actually needs no introduction. We can see that the material has a very unique property. That is, it can be found in a different allotropes and different hybridized state, sp3, sp2, sp, and especially the sp3 and sp2 hybridized states are of importance because they show a property that is completely contradictory to each other. For example, that is the sp3 diamond is the hardest material with a very wide band gap, and in the contradiction, sp2 hybridized graphite is a lubricating metallic character, zero band gap, two-dimensional, and carbon has another unique property that it can be found, it can be tuned in every possible shapes, like a zero-dimensional quantum dot, one-dimensional carbon nanotubes, or two-dimensional graphene, and three-dimensional diamonds, and other all. So, in the advent of nanotechnology, when in the year of 1991 the carbon nanotube was being discovered by Aichima, the entire research and technical community was jumped in joy to see that the material has a tremendous scope in different applications that include solar cell, sensor, field emission display, gas storage device, drug delivery, hydrophobic coating, and many others. But soon that effort came to a pause when it was realized that though the material is very effective, but at the same time it is very difficult to synthesize, especially with a very high yield and with a very large scale. The material needs a complex experimental technique, needs a very high temperature, pressure, the inert atmosphere, the catalyst support, and when even the every ideal experimental experimental what to say requirement is achieved, the yield is very less. So it was necessary to find a suitable what to say alternative of this material where the property of the material will be remaining intact, but the synthesis technique will be very simple and with a very high yield. Now, the possible solution was a amorphous analog of the carbon nanotubes and the amorphous graphene. It is a bit old work that I am representing. The experimental is very simple. You just mixed material A and B, that is the ferrocene and ammonium chloride, with a particular ratio, heat up at a 200 degrees centigrade for 30 minutes. Your material is ready. Just make it cool naturally, wash with deionized water and dilute HCl, then filter and dry it overnight at a 60 degrees centigrade. Your material is ready. And this is the basic experimental steps that I have shown. That's the ammonium chloride, ferrocene, taken in a mortar, mixture, taken in a beaker, heat up, and ultimately, after the washing and filtering, you can have your carbon nanotubes ready. And this material, when just go for a 2 hours ultrasonication, it gets readily unzipped to produce the graphene-like structure. And we have named it amorphous carbon nanotube, that is ACNT, and amorphous graphene, that is AGS. And one of the very inherent difficulty in handling carbon nanotube is that being a very inert, it is very difficult to make it vulnerable to the other material, just to functionalize it, to make it hybridized so that it can be used in the different applications. However, this amorphous analog of this carbon nanostructure having inherently large number of defects, they do not need any external acid functionalization for introducing the groups like hydroxyl or the carboxylic acid. They can readily interact with the other materials, and the different hybrids or composite is very easy to be formed. This is the basic acid functionalization process that no need to be done in case of our amorphous analog of the carbon nanostructures. So next is for the resultant discussion. Few basic results I am representing here. You can see the XRD part of our amorphous carbon nanotubes. It's completely featureless. However, a small hump near around the 26 degree to theta Bragg angle can be seen. This is the very well-known 002 peak, 002 plane of the hexagonal graphite. And from the FSM image, the one-dimensional structure can clearly be seen. Here also from the picture D, the tubular structure can also be clearly visible. And this the TAME image, you can see the nice one-dimensional structure, uniform structure with the diameter around 80 to 120 nanometers. This is from the SAD pattern also, the amorphous nature is clearly confirmed. And this is the Raman spectra. Both the D and G bands are clearly visible. And when these amorphous carbon nanotubes are unzipped for just 1 hour to 2 hour ultrasonication, this gets unzipped, and graphene-like two-dimensional structure can clearly be seen. And with this, we can produce a very good CNT graphene composites that shows very good cold emission property, and you can see that it is already published in a journal Carbon. And as I told you that this amorphous carbon nanostructure, they don't need any external functionalization for being functionalized with the other materials, foreign materials. I'm going to show you some basic hybridized sample we have got. This is a manganese oxide CNT hybridized. You can see that just by immersing our CNT in a KMnO4 solution for around 30 minutes and then drying the sample, we can have very good MnO2 flex functionalized CNT. And this work was published in Applied Surface Science. And this is the MOS2 CNT hybrids that we have got, in our lab by simple hydrothermal technique, where the L16 was used. And this is the zinc oxide flowers-like structure and zinc oxide triangle-like structure that you can see, that is very uniformly attached with the wall of the carbon nanotubes. So in every cases, very well dispersed functionalized sample can be possible to synthesis, which is almost impossible in case of crystalline CNT unless you go for the external functionalization. This is a SNO2 CNT functionalized sample. Now, from the very beginning, CNT is proved to be a very good cold cathode emitter. And what is the cold cathode emission? We know that there are 4 particular technique by which the electron can be taken out from the material surface. First, by applying the energy in terms of photons, what we call the photo emission. Second is by when we apply the energy in terms of the heat, we call the thermal emissions. Then by impacting with the electron with higher kinetic energy, we call the secondary emissions. And lastly, by applying the field emission, that is by applying the electric field. However, the last is completely different from the other 3 because here the emission of electron can be possible to achieve with the energy much lesser compared to the work function of the material. Why? Because in this particular case, instead of jumping over the barrier, potential barrier, the electron basically tunnels through the barrier. So it is called the tunneling phenomenon and completely quantum mechanical. And that is why it is also called a cold emission phenomenon. And I am not sure if the animation will be there or not. I mean, just trying to run. So the tunneling phenomena can be visualized in that way. That is, the man is running scared by the demons, and then it comes in the opposite side of a very high wall, and thinking that the demon cannot jump over the barrier, and he's basically very relaxing. But with its surprise, he sees that instead of jumping over the wall, the demon is basically come through the wall. That is the niceness of the tunneling phenomena. So, what is the basic principle of the field emission display? Here, the number of sharp emitters are there, and then when electric field is applied, the electron gets emitted by the process of cold emission that just I have discussed. And there, in the other way, the phosphor screens are there with the basic, 3 fundamental colors of red, blue, and green. The when the cold emitted electron falls on the phosphor screen, they produce the color, and with the mixture of all these particular colors, the entire color gamut is produced. This is the very basic equations we call the Fowler-Northam equation, which is used to analyze the field emission data. And here it is. You can see I is the current, A is the emission area, and beta is the enhancement factor, phi is the work function. Small a and small v are the Fowler-Northam constant, and all the VF, TF are the slope and intercept correction factor. So, of which most important is the term, that is the beta, which is the enhancement factor. What is the basic mechanism of enhancement? We just have seen that we just have told that in the cold emission phenomena, the electron is getting emitted at an energy much lesser than the the work function of the material. So it can be visualized in the way that at a very sharp nano tip of the material, the number of the electric field lines are basically getting concentrated, just the way the thunder is getting concentrated on the sharp tip of the like thunder shield kept in the high rise building. So this is the same way. That means the effective field is enhanced much higher than the actual applied field, and the effective field to the applied field ratio is nothing but the enhancement factor. Now we have done some field emission analysis of our system. You can see that this is so how much time we have?
Please wind up in 2 to 3 minutes.
Okay, so this is the field emission curve of our field synthesized sample. This is, you can see that the carbon nanotubes in amorphous form. This is the graphene in the amorphous form, that is HES, and last is the SANT AGS, the hybrid sample. And you can see that due to the wrinkle effect of the amorphous graphene, the field emission is very high compared to the all other pure samples. The same thing has been deposited on the carbon cloth to make it a flexible emitter, and here the turn-on field is obtained at a electric field lesser than the 1 volt per micrometer ratio.
No one
And this is the same thing. This is the same thing we have got from the zinc oxide CNT sample, and we can see that due to the number of effective emission sites in for the hybrid sample, the field emission is much better. That can be evident from the turn-on field as well as from the enhancement factor value. And also this is the MnO2 CNT sample. You can see here also the hybrid sample gives much better emission. This is the stability curve of our sample. Here also the hybrid sample is much more stable compared to the pure CNT. And this is the conclusion part. Different carbon nanostructures have been synthesized with a very simple solid state reaction. And this sample can be very easily functionalized with the foreign material, and that functionalized sample gives much better field emission compared to the with the pure samples. And here the the effectiveness of this amorphous analog of the crystalline CNT or graphene is achieved. And this is the funding agency. I'm acknowledging with gratitude the DST SAR, that Tirthankar Mahavir University, Seed Money Scheme, CSIR, Jadavpur University for giving some basic experimental facility. Here are some few PhD students showed up: Devabrato, Shudip, Dimitra, Deepshikha, Unmesha, Pratyusha. Thank you and Happy New Year.
Good afternoon, everybody. Myself, Garima, from Vanasli Vidyapith, Rajasthan. Here I am going to present my work entitled Tuning the Structural and Dielectric Properties of Zinc Ferrite through Varied Annealing Temperatures. Objectives: as ferrite are the promising material for various technological applications like magnetic storage devices, electronics, ferrofluid technology, magnetocaloric refrigeration, and biomedical applications, sensors, catalysis, etc. So our main objective is to synthesize low-cost zinc ferrite without alternating the PS solution, followed to investigate the possibility for improvement of optical, dielectric, and other properties like magnetic catalytic as a function of annealing temperature. Synthesized zinc ferrite. The nanocrystalline zinc ferrite was synthesized by sol gel method using iron and zinc nitrate as starting material and citric acid as fuel. This figure shows that the synthesis process followed by the characterization techniques used initially, the metal nitrate and citric acid were dissolved in distilled water in 1.1 molar ratio to form a mixed solution. This solution was kept on a magnetic stirrer with a hot plate. To obtain precipitate gel, the powder form is obtained by achieving auto-combustion process at 150 degrees centigrade. The obtained powder was thoroughly ground in an agate mortar and dried at room temperature in furnace. The dried powder sample was annealed at different temperatures 200, 400, 600, 800 and 1000 degrees centigrade for 6 hours in the air atmosphere, which were used the different measurements. The powder X-ray diffraction pattern of zinc ferrite annealed at different temperature are shown in this figure. It shows that the broadening of diffraction peaks decreased while the intensity of diffraction peak increased with increasing the annealing temperature, which confirms the formation of crystallinity as increasing the annealing temperature. We have done ritual refinement of the XRD patterns using the foolproof suite software to find the structural parameter, ritual refinement, X-ray diffraction pattern of nanocrystalline zinc ferrite powder annealed at different temperatures shown in part A, where the profiles calculated from the fitting procedure are displayed as a continuous line while the symbols are the experimental points. Part B shows the Williamson hole plots of the nanocrystalline zinc ferrites synthesized at different annealing temperatures. The crystallite size is calculated using y-intercept of the fitting of the Williamson hole plots. The FTIR spectra of annealed zinc ferrites in the wave number range 4000 to 400 centimeter inverse are shown in this figure. It shows that both the principal absorption band of spinal structure are observed in between wave number 600 to 400 centimeter inverse, which also confirms the formation of spinal structure of annealed lanthanum doped nanocrystalline zinc ferrite. Ritual refinement parameters along with the IR bands and optical energy band gap of annealed lanthanum doped zinc ferrites are tabulated here. It shows that crystallite size increases from 16 nanometer to 58 nanometer with increasing the annealing temperature from 200 to 1000 degrees centigrade respectively, which indicates the formation of crystallinity as increasing the annealing temperature. The observed reflectance spectra of zinc ferrite are shown in figure A, which show a slight change in reflectance spectra with the annealing temperature. The direct energy band gap value of annealed zinc ferrites are calculated using figure B, which demonstrate the the annealing temperature raised the energy band gap from 2.03 electron volt to 2.14 electron volt. This variation illustrates that when the annealing temperature rises, the energy band gap of nanocrystalline zinc ferrite move to the higher energy side. The variation of dielectric constant with frequency at room temperature for lanthanum doped zinc ferrites annealed at different temperature are shown in figure A, while the variation of loss tangent with frequency at temperature for lanthanum doped zinc ferrite annealed at different temperature are shown in figure B. In this figure, first panel show that variation of real and imaginary dielectric constant. Second panel show the variation of real and imaginary impedance, and third panel show the variation of real and imaginary modulus as a function of frequency at temperature of the annealed lanthanum doped zinc ferrite. These are the conclusion of my present history. I am thankful to the organizers for providing me this opportunity, and thanks to all for your kind attention.